Hi, I'm Zor. Welcome to Unizor Education. Today I would like to present a really simple problem, but it's supposed to illustrate the topic which I was discussing in the previous lecture, which is angular momentum conservation. Actually, I would like to present it as a kind of a practical situation. Then I will basically do some theory behind it, and then we'll return back to this practical example. So the practical example is if you've seen figure skating, then at some moment they're doing rotation with stretched arm, and then they're bringing the arm close to the body, and they're starting rotating much faster. Well, this is a perfect illustration of this angular momentum conservation law. So this is an example, but I will simplify it right now, and I will present a purely theoretical calculations. Well, calculations are really like one or two lines of code, no big deal. And then we'll return back to figure skating. So here is a physical experiment which kind of models this particular example of practical kind of usage of law of angular momentum conservation. Consider you have a plane, and within this plane there is an object of mass m rotating on radius r0 with angular speed omega 0. So this is the plane rotation within the plane. Now I would like to reduce the radius of rotation. How can I do it? Well, let's do it this way. Perpendicularly to the plane of rotation, I will put a small tube, and the thread on which this object is rotating, I will not end here, but I will go through the tube, and I can pull it. If I pull it, now the tube is perpendicular to the plane of rotation. The radius will be reduced, and that actually corresponds to this example of figure skating when it brings the arms back into the body. Now, what is the force which acts on this mass? Well, the force is the tension of the thread on which it's rotating, right? And since my tube is perpendicularly is positioned perpendicular to the plane of rotation, and it ends exactly at the center. So if this is a plane, this is a tube. So it ends exactly at the center of rotation. So the force which actually holds on the trajectory, on the circular trajectory, the force is directed along the thread, and it's always central, because my tube ends at the center, right? So it doesn't matter that I pull it up or let it go, pull it down or let it go up, doesn't really matter. The force will always be central. And in the central force, as we know, the angular momentum vector where r is the vector of position and p is vector of momentum, mass times speed. Speed is tangential. This is my speed. So this is preserved. So no matter what I do with this thread, if I'm pulling it down with a force, actually doing some work, it brings closer. If I'm letting it go a little bit, then the mass will actually start rotating on a higher orbit, well, on a further radius from the center. So it all depends, but in any case, this is supposed to be preserved. Okay, so if I pull it down to a certain other radius, let's say r, which is smaller than r0, what happens? Well, this thing is supposed to be preserved. Now, the speed is always tangential to the rotation, to a circle. So in the new position, which is somewhere here, it will still be tangential. That would be my v, and that would be my r, which is smaller than r0. So the speed will always be perpendicular to the radius, and that's why the absolute value of L, I'll put it just letter L without arrow on the top, would be equal to m r v. Since r and p, or r and v, are perpendicular to each other, the sine of the angle of 90 degrees equal to 1, so the absolute value, the modular magnitude of the vector, is just the magnitude of one vector times magnitude of another vector times sine of 90 degrees, in this case 1, so this is the magnitude. And it's supposed to be preserved, which is what? Which means it's equal to m r0 v0. Now don't forget that v is equal to r times omega. This is angular speed, this is the radius, and this is the linear speed on the circular orbit. So from which we can derive the m. So instead of v, I will put r omega. So it would be r square omega is equal to m r0 omega 0 square. From which r square omega is equal to r0 omega square omega 0. So my angular speeds of rotation are inversely proportional to the squares of the radiuses, right? Or, if you wish, omega is equal to omega 0 times r0 squared divided by r squared. So if my r is smaller than r0, so if I'm pulling it down so the r0 is smaller, then obviously whenever this ratio is calculated, it will be greater than 1. And don't forget, this is a square, so it's even greater than just plain ratio. It's inversely proportional to a square of the ratio of radiuses. So basically, this is the physics behind changing the radius. You change the radius, let's say, by half, your rotation speed, angular speed of rotation increases in the factor of 4. So radius half, rotation increases by factor of 4. So just imagine if you would like, for example, to put the satellite on the orbit around the Earth. If you know the radius on which you would like to really put this particular satellite, you can very easily calculate the speed. Actually, we did it at some time in the past. You can calculate the speed on which it's supposed to be rotating. Speed, linear speed or angular speed. If you want it closer to the Earth, it should really spin faster to hold the orbit. Okay, so that's basically the simple physics behind this rotation with a changing radius. Now, so let's get back to figure skating. Figure skating just a little bit more complicated because it's not just one particular body which is rotating on the certain radius, it's two different things. One is your main body, which is rotating, and another is the arm which you're pulling towards yourself. So it's two different, let's say, objects which are independently rotating. One of them is changing the radius, the arms, but the body is still the same. So basically, let's just imagine that you have M is arms, and capital M is the rest of the body. Everything without arms. First, it rotates with initial angular speed omega, with arms stretched. So it's rotating, and then it brings the arms back, and it's supposed to rotate a little bit faster with angular speed omega, which we are going to calculate. So what is this? Well, first of all, initial angular momentum is angular momentum of two different things, arms and body. The arms are m, let's say r0 square omega 0, where r0 is the radius of rotation of arms. Well, probably somewhere in the middle of the arm. That's the radius. Obviously, it's much more complex. I mean, we're trying to avoid more complicated things. So we're considering that the mass of arms concentrated in the center of mass. So, and the radius is r0 of rotation. Now, with the same angular speed, our main body is also rotating. Now, the radius of rotation, again, we will have something like a middle radius of the body. It will be r, capital R square, omega 0, same omega 0. Now, when we bring the arms towards the body, now the arms will be on the same radius. Instead of r0, it will be in radius r. And by the way, r0 is greater than r, obviously. Radius of rotation of the arms is greater than the body. So now this is supposed to be total angular momentum after we brought the arms towards the body. Now it's one body, actually, one object, which has a mass m plus m, rotating with the same radius as before, r square, but with a new omega angular speed, from which we can very easily derive the omega, which is m r0 square plus r square omega 0 divided by m plus m r square. So that's the formula, where m is mass of arms, m capital is mass of the rest of the body, r is radius from the center of rotation to, let's say, the middle of the body, somewhere, I don't know, and r0 is the radius of initial radius of rotation of the arms, again to a center of mass of arms. So put your numbers and you will get the final. Now this is obviously greater, since capital R is smaller, then this expression is bigger than the bottom. So we are increasing, omega 0 will increase to omega, some factor, whatever the factor is. Well, that's it. Now, I do recommend you to read the notes for this lecture. Well, the notes are on Unizor.com. You choose Physics Plus course. Now, this is the topic called Laws of Newton, and within it would be the problem number 4. Now, this Unizor.com website contains other courses as well, which I do recommend you to take. For example, Mass for Teens, Mass Plus, which is kind of a little bit above, Physics for Teens, again little bit more than high school, but then there is a Physics Plus, which is even a little bit further, and some other courses like theory of relativities, for example. Well, introduction into theory of relativities for people who would like just to be introduced into this theory, and some others. Okay, so that's it. Thank you very much, and good luck.